So let me first maybe introduce myself. My name is Ignacy Kowalczyk. I'm engineering manager at Google, and I came here from Warsaw, Poland, where we have engineering office working on cloud. So we got around 200 engineers working on various cloud technologies, mostly around compute. So we don't do storage, we don't do machine learning, we do compute. The topic is this, cloud native. There's kind of a buzzword recently, especially in the cloud space. So I will be trying to a little bit demystify it during this presentation. But before I get into the details, let's take a look at some history. So how people were doing computing in the past. Maybe some of you still remember the old times of shared machines where companies were buying huge mainframes, big servers, and then they were putting lots of stuff on that. And obviously that wasn't easy. There was no isolation, one process deployed to this machine, let's say, misbehaving could allocate a lot of memory, and then the other processes would be kind of starved. Also dependencies. So you might have heard the term DLL hell. So every application required some different flavor of libraries, maybe different versioning, and that was an issue and kind of a nightmare for sysadmins as well. All right, so that's why people came with this idea of virtual machines. So the idea was very simple. Virtualize the hardware and run basically specific applications in very hard sandboxes, which are virtual machines, which are running separate operating system. So basically, sysadmins could kind of carve out the exact amount of resources, RAM and CPU, for individual applications, and also kind of prepare the operating system image especially for a given application, right? So that obviously solved the issues of isolation and dependencies. However, it's super expensive and kind of heavyweight, right? So every single application required, or every reasonably sized application with lots of requirements required like a separate VM. So that's obviously comes at a cost of spending additional resources on computing power for the operating system, and also well, the VMs don't start fast, right? So that's kind of a booting time. Basically, the environment is not that agile. So let's take a look whether we can improve anything on this picture. So this is like the regular stack with VMs. So you have 3 virtual machines. Each machine is running guest operating system, has some libraries, and obviously has the applications that you want to run within these virtual machines. And as you can see, obviously operating systems are kind of redundant here. So how about we cut here and we build something like that? Can we do it such that these 3, how we call them here, containers, provide enough isolation so that these applications can run safely, and then these applications can come with any sort of dependencies they need? So yes, we can. That's basically the idea of containers. I hope you've heard about containers. Like, who didn't, or like, who heard about containers? Awesome. Over half of a room. That's great. So, but what this really is, containers, it's first thing, it's like the way of packaging the software together with all the dependencies, so that you kind of include all the libraries that you need in a package. And second of all, running it in the as isolated processes, so that they actually cannot steal resources from each other. By resources, I mean compute resources, so RAM and CPU and maybe local disk also. All right, so how do we do this? So this is a picture of a Google data center. And Google obviously many years ago, when most of the other companies were still in the kind of virtual machines mode only, or even shared machines, we wanted to use containers because we wanted to kind of save some costs. At our scale, this really matters, whether we're running everything in individual VMs or whether we can actually run containers, which are basically Linux processes, so that's much more lightweight, right? So how do we do this? So we wanted to run, containers on all these big data centers, and the question was again, how do we make it so that these containers do not steal resources from each other? So that's why Google engineers introduced the concept of control groups in Linux kernel. That's kind of a small, short snippet from Wikipedia. So control groups is basically a feature of Linux kernel that allows setting up processes in a way that they have limited access to CPU, RAM, and together with other Linux features such as namespaces, you can pretty much quite well isolate processes within the operating system. So not only there will be isolation in terms of CPU and RAM, but also isolation in terms of file namespace or networking namespace. So that's how basically we helped Linux to provide this containers feature. So many years later, fast forward ahead, there came Docker, and Docker made it easy for people. So up until then, before Docker times, obviously you could do containers, but A, there was no standardized method to package container images. B, it was quite difficult to actually set up containers in Linux environment. So you had to be kind of Linux hacker to know how exactly set all these C groups for your processes. And Docker made it super simple. So there's a declarative YAML file. You put all your requirements in this YAML file, and Docker takes care of basically setting up all the environment for your process, or for your container, actually. Plus, they also introduced the concept of container registry, so it's easier to do kind of CI/CD integrations. All right, so basically with containers, you have a third way, which is, we believe, superior. So basically, kind of back to the shared machines, however, running processes in isolated containers. So what are these benefits of containers? Apart from the cost efficiency that I mentioned, so that we don't have to run the overhead of operating system for each application, it's also super portable because it includes all the dependencies. It's also, it provides also versioning. And the last actually bullet here is super important, fast deployment. So again, virtual machines have to boot up. Containers is basically as lightweight as starting a process in Linux. So that's super useful for modern applications where you need to react fast to changing environment. Let's say do fast upgrades. Let's say do fast scaling if more traffic comes into your application, etc. So this is that's why actually containers are a fundamental building block of cloud-native applications. And so at Google, we basically adopted containers very broadly. So basically everything that runs at Google runs in containers. So we execute something like 4 billion containers every week. So with this scale, obviously there are some challenges. So how do you actually run 4 billion containers every week? Like how many people do you have to employ to do all of these container executions, right? So actually we need to automate it. We need to have an environment that manages execution of containers, manages updates of containers, manages how many replicas of each container we need depending on the needs, how we monitor these containers, and how we provide security. All of these aspects are super critical. This is not something that Docker solves for us, just as a tool to basically build containers and execute containers. So that's where we are approaching basically how we do a so-called cloud native at Google. And this is, a lot of that is about container orchestration. So basically, I joined Google actually something like 11 years ago. And the first thing I've learned is that if I want to run my application in one of the Google's data centers, it's actually super trivial. I have to provide a short snippet of configuration file that will tell our container orchestration system, that's called Borg, how to execute my process. And so let's take a look how it looks like. So basically, my probably first application was obviously Hello World. So I need to only provide the name of the cluster. Basically, let's think of it as a data center. where to run my application, I need to point the Borg to where my binary is. I could provide some command line parameters, that's kind of optional. And then I had to provide the requirements for CPU, memory, RAM, disk, and CPU. So that actually Borg will set up my application in a container that will be limited to use only this amount of resources. Finally, I could provide a number of replicas. So why not put 10,000? It's basically when you design applications to be cloud-native applications, you design for scale. And so all the systems have to be prepared to running at basically arbitrary large scale. So actually this is as simple as that to run 10,000 copies of your process. And you don't need to SSH to 10,000 machines. The container orchestrator will do it for you, will find the machines that can run this stuff for you. So then what happens when you execute it? So let's see. So this is like a don't be scared. It's actually quite trivial architecture. This is architecture of Borg, our container orchestrator. So basically our data centers, in our data centers we run Borg. Borg manages all the machines in our data centers. Actually there's a concept of Borg cell because we divide our data centers into kind of smaller units, which are basically failure domains. But Borg has also some scalability limits. And so my binary hello world is up there. My simple config file that I just showed you is also up there in the left top corner. And then I use Borg config utility, and I only need to talk to Borg master. I don't have to, again, SSH to any of these physical machines that are down there running an agent software of Borg called Borglet. I only need to talk to Borg master. Borg master is obviously replicated for availability. So the first thing that's happening, my binary gets pushed to the cloud, in this case, our private Google Cloud. And then next thing I'm telling Borg master, hey, I need 10,000 replicas of my application. There is a scheduler in Borg master that observes like what's the intended state of what I'm doing basically with the system. And then it finds machines in the data center or in a Borg cell that still have enough room to accommodate my application. So remember, I put there this number of CPU, number of RAM. So basically, this stuff is kind of bin packing algorithm. So my binary is getting pulled from the repository and executed on node machines. So and that's what's happening. I got 10,000 hello world started in a few seconds, basically. Somewhere in a huge Borg cell. Okay, cool. So, with containers and container orchestration tools such as Borg, give you simplicity of deployments and also agility of deployments. But to write cloud-native application, maybe let's try to define it a little bit better. What is this cloud-native application? So that's the application that's So the requirements that you have for cloud native is basically more holistic, let's say, right? So we want to be able to develop fast, and we want to be prepared for arbitrary traffic spikes. So you don't want, your application to be the victim of its own success. If you have many users, it should just scale. And also, you need to basically, in the modern times, like in business, you need to move really fast. So you want to have fast iterations, you need to deploy really fast. So you have to have a very short cycle of, commit into code repository to deploy to prod. So you want to have really automated CI/CD pipelines. So it's also about that. And finally, these applications, with scale, they still have to be highly available. So you can't afford basic failures, right? So how do you design such applications? So unfortunately, it's not only about like DevOps only and how you deploy them, but also how you architect them and how you design them. So that's why actually developers also need to think about how do I design my cloud native app. So first of all, obviously, you should be using containers for all the reasons that we have already mentioned. But it's more than that. It's good to design your applications so that they are decomposed into microservices. You've probably heard this terms many times, but this really works. Like, when I joined Google, I was kind of surprised by this first tech talk, which was Life of a Query, when I learned, how many services are actually taking part in this, serving path for this single web search query at Google, which is kind of, returns results in milliseconds, right? And there's still lots of microservices. So why do we do this? Well, development velocity is first of all, right? If you don't have big monolith, it's easy to get your tests right and, push your new version of software to, staging and prod environments. Obviously, next thing is limited by blast radius. So if you have something crashing, you're crashing just one small service and actually one replica of one small service, not like a big binary that handles many more tasks. Lastly, you have efficient autoscaling. So imagine you have two methods. One is CPU intensive, one is RAM intensive. If you combine them into one process, and you're scaling your containers in terms of how much RAM, how much CPU you need to them, and how many replicas you need, if suddenly there is more traffic to one service, you need to scale it by providing more replicas, and you are suddenly starting to produce a waste on the other dimension. Let's say if the CPU-intensive method needs scaling out, you're going to lose RAM. So that's why microservices are important. Next thing, design your software so that it has stateless processes. Stateless processes enable much easier adoption to scale, so scaling. If you have more traffic and your service is stateless, all you need to do is basically run more replicas. And with container orchestration, running more replicas is as easy as changing one line from 10,000 to 20,000 replicas. Boom, in a couple of seconds you got it. Obviously that's how it works at Google, but I'm going to tell you later what's available outside of Google as well these days. And and in general, your process has to be kind of disposable compute unit. At any time, it can be rescheduled somewhere else. Remember that at this scale, failures are kind of a norm. Right? If you're running like tens of thousands of replicas, you're going to have failures, even because of CPU problems, hard disk problems, whatever. It's like inevitable. So again, stateless services are very easy to auto-heal. Well, obviously, you cannot get rid of state totally, so you still need to have some storage. And for that, you should be pushing all the state as much as possible to the backend databases. And these databases, like MySQL, like a regular one instance MySQL at least is not a good cloud-native database. It doesn't scale well. So you should be using replicated distributed storages. So a good pattern for a cloud-native storage is it's distributed so it can accommodate higher scale by having more, we call them shards or partitions. And then in the second dimension, these partitions should be also replicated for availability and durability. So there's a number of actually options down there. So Google provides Cloud Spanner, for instance, but you also have like open source tools that you can try using, like maybe Cassandra, and also there is Vitesse project, which is sharded MySQL. So there is different options out there. Obviously, all these different options have different guarantees. So, for instance, different integrity constraints. And CAP theorem is an interesting thing that I'm kind of trying to, kind of put it on my slide so that you learn a little bit about it. So I kind of encourage you to read about it. It's quite cool stuff. Finally, separation of development and operations. So this is something that is super important. Developers just write code, and there's different functions that are taking care of security, of actually maintaining the production environments. And again, in the cloud-native world, we should make it so that it's not like a developer who takes care of, let's say, security of their deployments in production. And I'm going to talk about the tools that actually allow this. All right, so how do we do this cloud native if you're not at Google and you don't have Borg? Okay, so let's take a look at the sample case study. So this is like not a real company. Let's imagine there is a Dynacorp company, and let's imagine that we have 3 roles there in this company. There's Erin, the developer, John, the sysadmin, and Sam, the product manager. So Erin learned about the containers. Docker is super popular, as we all know, so that should be of no surprise to anybody. She loves it. There's no problems with dependency and portability. She can easily deploy her container she develops on her machine or in various other environments, staging, prod, etc. John, the sysadmin, is not quite happy about it, actually, because this is what is happening with containers. So there is, and with cloud native approach in general, like developers formed many groups building microservices, and instead of, let's say, one big monolithic release every month, they are right now expecting that they'll be able to do like 50 different services being rolled out, a couple of times a day to prod. So obviously, this is not something that John can do by himself. So, but Erin told John, hey, there is Kubernetes. So, and let's see what is Kubernetes. And by the way, Kubernetes is the project that I'm actually working on in Warsaw in Google. So on the left side, there is Borg logo. On the right side, there is Kubernetes logo. And you remember this picture, Borg, so basically a Borg master that takes care of scheduling your containers on a large pool of physical machines where it just needs some agent software called Borg to be running there. Well, this is Kubernetes. So that's very similar, actually. We just renamed some concepts. There's kubelet, not Borglet. There's Kubernetes master. There's container registry. There is container image instead of a regular binary. And there's kubectl instead of Borg config. So Kubernetes actually was built by Google. The project started like 5 years ago. And well, we open sourced it something like 4 years ago, as far as I remember. And right now, Google is not even Google is a major contributor still, but it's like less than 50% of overall contributions. So Kubernetes became kind of a Linux of cloud. And so on Kubernetes, it works very similarly, actually. So, you want your container image to be pushed to the container registry, and then you talk. Then the users talk only to Kubernetes master, gain declarative config stating, I want my container to be running in some amount of copies. And the scheduler finds nodes, and the image is pulled from the repository to those nodes, and it's executed. A little bit simpler view of that. So basically, there's Kubernetes master, which runs API server, and all the users connect to API server. The storage, the persistent storage of Kubernetes is an open source distributed key value pair storage called etcd. And you've got all your nodes, which are typically, that can be, Kubernetes can work in various scales. You can deploy Kubernetes to your machine, to your laptop, and have one node cluster. Or you can use Kubernetes in public cloud environments and use as many as, it scales up to 5,000 nodes currently. Okay, so what Kubernetes, we didn't just, copy all the ideas from Borg. We actually also applied some, learnings. So not everything worked that nicely at Borg, and we try to be better with Kubernetes. So first of all, we have decomposed the Kubernetes master, so it's very extensible. So basically, right now, what you can see is there is a lot of projects, even on GitHub, there's like a few hundred projects that are extending Kubernetes with their new APIs, new so-called resources that you can basically plug into the API server and provide your own controller that will actuate, all the stuff that you want to do in your API. So examples of controllers in Kubernetes is scheduler, deployments, autoscalers, load balancers. I'm going to talk about Istio project soon. This is also extension of Kubernetes. It also takes advantage of extensibility of Kubernetes. So next thing that we changed in Kubernetes, your containers are actually so-called pods, which are a vertically integrated set of containers. So a pod can be a single container or multiple, but this is a basic scheduling unit. Have their own IP addresses. which makes it even better isolation, right? So imagine you have an application code which hard codes opening port 80. That's a problem. If you want to have some scheduler to put these two applications on the same machine, they will not be able to open port 80 unless it's Kubernetes. Then they can, because they actually have separate IP addresses. Finally, there is this cool concept of labels and selectors. So in Kubernetes, labels are kind of arbitrary key value pairs that you can but they can basically annotate every object with. And then you have a powerful notion of selectors. So you can have, like, in multi-dimensional space of labels, you can do all sorts of queries. So that's, again, something that wasn't there in Borg. But John says, okay, so what? So this is what is happening so far. So in the past, all these users, all John's developers were basically talking to individual nodes. Now they have a Kubernetes master. They talk to master. Nodes are hidden. Utilization of these nodes is provided by the master. And also, within the company, John could introduce, like, the somehow standardized CI/CD pipelines. So basically for building and deploying software on Kubernetes clusters. There is other problems that Kubernetes is solving. It's not only about deployment of containers and scheduling them on nodes and bin packing, the resources. So it's also about, like, scaling, for instance. So Kubernetes has the capabilities around auto-scaling applications. So to automatically actually adjust the number of the replicas of your containers that are running, depending on either CPU utilization or maybe some custom metrics that you want to use, such as QPS from the load balancer, or number of messages in the queue, whatever you like. And by the way, auto-scaling is the feature that we're building in Warsaw, so if you're interested, I can talk a lot about it. Also, we auto-scale the Kubernetes clusters. So if applications needs to grow because there is more traffic, suddenly it may turn out there is no room in the cluster, so cluster needs to grow. That's obviously possible in cloud environments. So, at Google, you would just, add more virtual machines. But even if you're running on-prem and you're putting it on top of, let's say, vSphere environment, you can still dynamically adjust the size of your clusters. There is also a lot of other features that Kubernetes provides. I will not be doing, like, the training on Kubernetes here, but I encourage you to look at it. All right, so next thing. So I mentioned that cloud native is not only about the deploying containers onto the nodes. So let's go back to our DynaCorp company. And remember, Sam, product manager, Sam is super happy because his developers just got, like, a new feature prepared to roll out to production. And here's how Sam wants to do this. Sam wants to basically, do it in a kind of controlled way. So basically, he wants to roll out this feature to only, like, a small fraction of the users. So how to do that? So Sam heard Istio can help with this. And Istio is a project that, again, this is like an extension to Kubernetes. It's part of this bigger ecosystem of kind of cloud-native solutions around Kubernetes. So Istio was built to help manage microservices. By managed, I mean here connecting, securing, and monitoring. That's really what it is. And let's go one by one what it actually means. So in a regular service architecture, you would have these, front-end, out, pictures, payments, whatever services that you did in a cloud-native way, microservices deployed in containers, running Kubernetes clusters, and they talk to each other. And then and what Istio is doing is Istio is taking advantage of extensibility of Kubernetes and actually is adding a proxy service to each of your containers, or actually to each of your pods. So it's using some Kubernetes magic, so every time your pod is being deployed, the extra container is getting injected into your pod that's actually an Envoy proxy. And then what is happening, these services not talk to each other directly, but through these proxies. So all the communication is through proxies. It's like front-end talks to proxy that's inside their pod, and then this proxy talks to another service. So what it gives us, like the Istio can control a number of aspects of this communication. So first of all, discoverability and configuration of these services can be managed by Istio, and basically the load balancing is managed by proxy and is basically configured by Istio. Second of all, you can do security. So the code, the developers of the services don't need to care about that. It's actually declarative configuration on the proxies, and we'll take a look at it in a moment. And also monitoring. Since all the traffic flows through proxies, proxies can gather a lot of interesting data about the network traffic between your services and can actually export these metrics for you. So let's take a look at the rollout of the new feature. So the steady state, you have your service, you have the users contacting this feature, and then you want to roll out the new version, a canary. So that without Istio in Kubernetes, you would need to, if you want 10% of traffic to go to your canary version, this is how you would have to do it. You would have to have like 10 replicas and 1 canary. And with Istio, you can actually configure, Istio has kind of better traffic shaping features. So you can have 2 replicas and you can still configure Istio so that 10% of traffic goes to 1 replica and 90% to the other. And this is how it's basically as easy as it is in the configuration for Istio. And obviously, envoys are configured properly for that. There is also more advanced traffic shaping features available, such as you can route the traffic depending on the user agent. Like this example, we have like a new version of our application that's specifically improving the experience of, let's say, iPhone users. Okay, so like now John is happy. You can see a lot of the benefits of Kubernetes and the whole cloud-native ecosystem around it. And now let's see, like new person shows up in the company, new requirement, security. Marina's our CFO, she doesn't want this communication to payments gateway to be non-secured. And again, like Istio can help, developers don't need to do anything. The sysadmin just reconfigures envoy proxies to use TLS communication. So you don't have to care about all these things like certificate rotations and anything. It's all dealt with by Istio. So as I mentioned, traffic control is like the most obvious feature. Security is another very important thing. Observability is also important. Hybrid cloud is an interesting one, actually. Hybrid cloud means because all of this Istio, Kubernetes, these are all open source systems. You can run it in your on-prem data center, you can run it in Google Cloud as managed services. And you use the same APIs, so you deploy the same way, CI/CD pipelines to on-prem environment and to cloud environment, or maybe even to multi-cloud environment, so on the different cloud providers. So that's like the huge benefit of using open APIs. And if you're interested, there is like this cloud native computing foundation, and there's more projects inside it. Kubernetes is like the most important project that's run out of cloud native computing foundation, but there is more. Like Prometheus, for instance, is a monitoring solution. Prometheus is open source project based on the idea of Borgmon, the monitoring solution that we used at Google many years ago. Right now we have a little bit more modern solution. So similarly as Kubernetes is based on Borg. gRPC, of course, like this, similar to the way we are doing RPCs at Google. So I'm not going to talk about it, but please take a look at their webpage, Cloud Native Computing Foundation, lots of cool stuff there as well. So, before actually I say thanks, I just wanted to kind of wrap up a little bit. So, cloud native is not on, the idea of cloud native is how to write your software and also how to build processes in your company so that you can write software in a very agile way, very efficient way, have short cycles, commit to prod, and make your applications prepare for scale. So if your company is a big success, you will not have to re-architect everything. And so you have to be designed for high availability and high scalability, and having high agility since the kind of inception of your project. So that's why you need to think about the tools for deployments, for managing the production environments, but also about how you architect your software. And there's a bunch of links down there, so I encourage you to take a look. Thank you so much.
Actually, you still stay here for a couple of Q&A questions, if you don't mind.
Yes, sure.
So I'm going to show you, you should be hearing me. I'm going to show you how you can ask questions now.
And also I'll be hanging around the whole day, so feel free to ping me.
Do, and you enter the hashtag of GG Sofia. And then you get to the page where people are asking questions. Cool. So those are the questions that are asked. Actually, some of the questions you should be ignoring because they're actually to the organizers, but there are two for you. The first one would be how the traffic between Istio proxies is secured as being network traffic, aka packages. If we use some encryption, the communication will be slow.
Well, okay, so the encryption is adding some kind of fraction to the latencies, but it's mostly about being CPU intensive rather than network intensive. And obviously this is optional, so you can always choose, and again declaratively in your config files for your services, which communication you want to be secured and run over TLS, which not, right? And obviously it's all managed automatically by Istio. So I hope it kind of answers.
Hopefully it does. If it doesn't, well, just ask additional questions clarifying on that. What is the smallest scale at which you think that using containers would be justified?
Well, I think it's good just to play with containers at any scale. You don't probably need to use, like all this, cloud native goodies in such as Kubernetes and Istio from day one. But if you'll be using containers, you basically get a lot of you can basically upgrade real easily, right? Later, as your scale grows. And frankly speaking, I see the users of Kubernetes who have like 3 nodes in a cluster. And one of the benefits is you have the Kubernetes is becoming kind of a standard APIs to deploy stuff. So you get a lot of toolings around it. So even if you don't have that big scale, like tens of nodes or hundreds of nodes or maybe even thousands of nodes, you can still benefit from all these, basically an ecosystem of tools if you're based on Kubernetes APIs.
Super, and then I think this relates to another question. Is Kubernetes an overkill for small projects that are just getting started?
As I said, I think it's not. I think it's, it's basically, as I said, I see users of, Google Kubernetes Engine that are running small clusters, couple of nodes, and they are still benefiting of all these other tools that are built as extensions to Kubernetes, right? So I think it's just for this reason it's useful.
Then it's one distinguishing question: how is Borg different from Kubernetes?
Yeah, so
better actually, it's the question.
Right, so I think I tried to explain a little bit on the presentation. I don't know if this discussion is still valid, but as I said, we tried to make Kubernetes much more extensible. That's one, and it worked. If you look at how many GitHub projects are there right now that are providing custom resource definitions into Kubernetes clusters, so basically Kubernetes API is expanded with new tools such as Istio and stuff. This really worked, and I think the other big difference is the networking in Kubernetes, which is quite an idea. So this idea that each pod, so each basically, let's simplify it, each container is having their own IP address, right? So this makes the network communication between the services running on Kubernetes way easier. And again, this is it enables, things like Istio, and also it enables full isolation. As I said, you can even, schedule the applications that, hard code opening the same number of ports, etc. It will still work. Basically, anything works here.
Okay. Once again, if there are further clarifications you need, just ask another one in Slido. We've heard before that everything at Google runs in containers. Aren't there still processes so sensitive you don't trust containers to run?
So basically at Google, most of the stuff that we run on Borg this is actually a very good question. So most of the stuff that we run in Google at Borg is our own code. And if it's not, we need some additional security boundaries. Because containers are good for isolation for resources and namespaces, but they don't provide that much security, right? So there's actually a number of projects that are providing more security into the containers, and one of the interesting projects that you can take a look is called Visor. That's again the software that's been built by Google inside. Initially, it's been used by basically our cloud products that were running users code, and Visor is right now open sourced. And what gvisor is basically, it's an emulation of Linux kernel. So it re-implements most, unfortunately not all, of the syscalls. And so, like, virtual machine is like a virtualized hardware. Gvisor is kind of virtualized operating system. So it's almost as lightweight as plain container, so just Linux process. Yet it adds another security boundary. So if there is like a vulnerability in Linux kernel, that you would have to have, kind of vertically aligned vulnerabilities across, gvisor and Linux, so that somebody could actually take advantage of that vulnerability in the Linux, in the kernel.
Okay, Dimitri, your question I cannot understand. Can you just repost it again? And then I'm skipping to another one. The computer is walked now, so I'm just going to read them through. Do you think that the end of virtual machine is coming?
I'm sorry?
Do you think that the end of virtual machine is coming?
Well, it's probably not coming super fast. Like companies have software that was developed like 20 years ago and still need to run it. So what we are seeing with our customers is that they have kind of combined environments. So so right now we are kind of estimating that something like maybe 10% of the workloads around the world have been containerized and 90% not. So there's like still quite a opportunity out there. But what companies are doing, they are kind of combining these environments. So they use virtual machines to run their old enterprise stuff, their oracles, etc. And then for modern development of new apps like agile development, they are switching to containers and Kubernetes. And by the way, things like Istio mesh can actually help you marry the two worlds. Like Istio is not limited to Kubernetes actually, so there is already implementations that are working on VMs, so you can get your old style application running on a VM, part of Istio mesh. Obviously, you don't have all the automations. You have to, somehow differently inject the proxy onto your VM, etc. But then, if you put this proxy there, it can become part of Istio mesh, and then you can declaratively configure and monitor the network traffic between the VMs and Kubernetes clusters, or services running Kubernetes clusters.
Okay, thank you very much. Actually, we run out of time for additional questions. As Ignacy already mentioned, he'll be around. Please do make use of the time so that you can ask him further questions. Now we have like 5 minutes of a break so that people that wrote for the workshops, they can go to the workshop room. The workshop room is on the upper floor. There are already notes that are guiding you there. Actually, because more people wrote for the workshops than we have spots for, like we already announced it, that it's first come, first serve. And Daniel is going to be helping you out to realize whether you'll be able to make a spot for the workshop. Thank you very much, Ignacy, for this. And this is Google Software Engineering Manager coming to Bulgaria speaking. That's very appreciated. Thank you very much for coming.